Now we've talked about some of these capillary hemodynamic differences, but what about changing the resistance of the afferent and efferent arteriole? What impact does that have on glomerular filtration rate? So let's kind of zoom out and look at big picture hydrostatic pressure coming into the kidney and then leaving the kidney. So coming into the kidney, you have high hydrostatic pressure in the renal artery, and then it declines quite a bit in the afferent arteriole. That kind of makes sense. But then you have kind of a relatively stagnant yet still high hydrostatic pressure in the glomerular capillaries. It declines again sharply in the efferent arteriole. And then it makes sense that hydrostatic pressure in the peritubular capillaries and then the venous system is much lower compared to the arterial system. Now you'll notice that we have two good sites of physiological regulation of hydrostatic pressure, and they are at the level of the afferent arteriole and the efferent arteriole. And you notice that there are big sharp declines in hydrostatic pressures here. Interestingly enough, the glomerular capillary maintains relatively high hydrostatic pressure, which is unusual. You would think of a capillary, look at the peritubular capillaries over here, as being pretty low pressure systems. But this glomerular capillary is a very special type of capillary because it's got to filter so much every single day that you need relatively high hydrostatic pressure within this capillary to keep up with all that filtration. And then the arteriolar resistance on either upstream or downstream from that capillary can regulate the pressure here. So changing Starling forces within the glomerular capillaries can influence glomerular filtration rate. And the way that you can change Starling forces is by regulating either upstream or downstream, either within the afferent arteriole or the efferent arteriole. So in this image over here on the left, this is depicting either constricting or dilating the afferent arteriole. If you constrict, you squeeze that afferent arteriole before you get to the glomerulus, then you're going to cut off a bunch of fluid that would otherwise enter in there. The hydrostatic pressure within the glomerular capillaries would go down. If hydrostatic pressure in the glomerular capillaries go down, GFR falls. Opposite of that, if you dilate and open up this afferent arteriole, you're going to flood the glomerulus with more hydrostatic pressure. If you flood it with more hydrostatic pressure, GFR rises. And then you have effects on the efferent side as well. If you constrict the efferent arteriole, which is downstream of the glomerular capillary, then you're squeezing this right here, then there's going to be kind of a backup pressure within the glomerular capillaries. That backup pressure increases hydrostatic pressure there, which raises GFR. Oppositely, if you dilate the efferent arteriole, then fluid is going to flow on through very quickly, and the blood pressure or the hydrostatic pressure within the glomerulus is going to drop, and subsequently GFR drops. Now, something that we constantly want to keep in mind is not only glomerular filtration rate, but overall renal blood flow going in and out of the kidney. So when we talk about changing hydrostatic pressure within the glomerulus, that's going to influence GFR. But the way that we change GFR is either going to be by constricting something or dilating something. And if you constrict something, overall blood flow going in and out of the system is going to drop. If you dilate something, overall blood flow in and out of the system is going to raise. So that is what this graphic on the right is trying to depict here. You have your normal system. Glomerulus is this big bubble. Afferent arteriole is coming in. Efferent arteriole is the pipe going out. If you vasoconstrict the afferent arteriole, that drops pressure within the glomerulus. That's what this picture is representing. If you drop pressure within the glomerulus, GFR drops. But because you constricted something, overall blood flow is going to slow down going into the kidney and out of the kidney. Therefore, we say that renal blood flow goes down. If you constrict the other side, then GFR would go up, but blood flow is still down because something is constricted. Overall blood flow is going down. Now, there is a situation where you have the opposite now. If you vasodilate the out pipe or the efferent arteriole, you vasodilate that. That's what this picture is representing right here. GFR goes down. Yet, renal blood flow has gone up because you opened up the pipe, more blood is able to get through than would be otherwise. Similarly, if you vasodilate the afferent arteriole, that increases pressure in the glomerular capillaries and GFR raises. But since you dilated something, blood flow overall has gone up. So when I ask you questions about Starling forces, you need to be able to picture in your mind's eye what is changing in terms of GFR, the pressure within the system, and then what is happening to overall blood flow going in and out of the kidney. Which leads us to what is called the famous water hose analogy. So this is a famous way that you can use to conceptualize this idea of squeezing or dilating the efferent and afferent side of the arteriole, and what impact does that have on pressure. So if you have high pressure coming out of a hose, then water is going to spray. If you have low pressure coming out of a hose, water trickles out. So this water hose analogy begins with kind of a spigot, the hose itself, and then water coming out. So this is representing blood flow going into the kidney and then blood flow coming out of the kidney. More specifically, blood flow going into the glomerulus and then leaving the glomerulus. Now let's say that you puncture some holes in the middle of that hose, and that is going to represent what gets filtered at the glomerulus. So now you have blood coming in, some blood gets filtered out at the glomerulus, and then some blood flows on through the kind of the out pipe of that water hose. So now let's say that you turn up the spigot, you open up the spigot and water comes flowing through as fast as it can go. If you imagine water pumping through this hose as fast as it can go, it's going to spray out of the little holes you punctured at a very high rate, and it's going to come pouring out of the end of the hose. So if you open up the spigot, you vasodilate upstream, then you're going to have blood getting flowing on out, and you're going to have a high filtration rate. Now instead of opening up the spigot, let's say that you step on the hose upstream of your filtration, then it's going to decrease the water getting squeezed out of your holes or decrease filtration rate, and it's going to decrease overall blood flow coming out downstream. In contrast, if you step on the hose downstream from your punctured holes, then that's going to increase the pressure within your glomerular area, and water is going to start spraying out those holes. Yet downstream, the water coming out the end of the hose is still relatively trickling on out. So renal blood flow is down, yet glomerular filtration rate is up. So this graph is showing you kind of a big picture changing the effect of hydrostatic pressure at different areas of the blood vessel system coming in and out of the kidney. Renal arteries, afferent arteriole, glomerular capillary, efferent arteriole, peritubular capillary, and renal vein. So at baseline, that's what this solid line is representing. You have relatively high pressure in the arteries. It goes down a little bit in the arteriole, relatively maintained in the glomerular capillary, down again in the efferent arteriole, and all the way down through the renal vein. If you vasoconstrict the afferent side, okay, the afferent arteriole, if you vasoconstrict that, which is what this little dashed line is indicating, then you're going to have a little bit higher pressure in the renal artery. You're going to have initially higher pressure in the afferent arteriole, but then hydrostatic pressure in the glomerular capillaries are lower than normal, and then by the time you reach the renal vein, it's relatively the same. Now, if you vasoconstrict the efferent arteriole, okay, that's what this big dashed line is indicating, then everything upstream of that has a little bit of a higher pressure than it would be normally. Upstream, upstream, upstream. Now you vasoconstrict the efferent arteriole, and by the time you get to the end of the efferent arteriole, it's dropped. Downstream now, it's going to be a little bit dropped compared to normal. Okay, so now we have, just to kind of summarize here, we've talked about what influences GFR. We've talked about physiological regulation of that in terms of capillary hemodynamics. So now let's ask ourselves, well, what's regulating the capillary hemodynamics? And that's what this LO is going to speak to. Essentially anything that vasoconstricts or vasodilates your afferent and efferent arteriole are going to impact glomerular filtration rate. Okay, so we have listed out here a number of vasoconstrictors and a number of vasodilators. There's a couple of things I want to point out. For instance, angiotensin II primarily constricts the efferent arteriole. If you vasoconstrict the efferent arteriole, that will raise GFR. This is particularly important during times of decreased renal perfusion pressure. Now, if you inhibit this process using an ACE inhibitor, that will tend to lower GFR. Something else to keep in mind, your renal blood vessels are richly innervated by sympathetics. Okay, sympathetics, vasoconstrictors. And I mentioned a couple slides back that there's going to be a powerful vasoconstriction on one arteriole compared to the other because of simply having more alpha-1 adenoreceptors existing on the afferent arteriole compared to the efferent arteriole. Okay, so strong stimuli may constrict arterioles and decrease overall renal blood flow and cause changes in glomerular filtration rate, but again, even local sympathetic discharge and circulating catecholamines will activate alpha-1 receptors. So previously we were talking about what regulates those capillary hemodynamics. Now let's talk about what is kind of the fallout or the outcome of regulating these things. First thing I want to talk about is a concept called glomerular tubular balance. This is actually a pretty simple concept, but it seems more overwhelming than it really is. Glomerular tubular balance is really this kind of natural effect of what happens in the glomerulus has a parallel effect on what happens in the proximal tubule, so they're balanced. So essentially when GFR raises, then you need to raise subsequently reabsorption rate within the proximal tubules. When GFR falls, reabsorption rate in the renal tubules falls. Now, there's three kind of big mechanisms that contribute to this: changes in pressure, for instance, in the efferent arteriole, increased delivery of solutes to the proximal tubule, and then just overall GFR fluid flowing through the proximal tubules can stimulate microvilli, which promotes sodium reabsorption. These are the kind of the big mechanisms behind this, and I'm not going to read this to you. Hopefully it makes sense after you read it to yourself. But over here on the right, I put the main kind of takeaways of what glomerular tubular balance is. It results in increased changes in pressure that increases GFR, results in an increased presence of oncotic pressure in the peritubular capillaries. If you're scratching your head right now, go back to that slide at the beginning of the lecture that had that graph of filtration fraction. And if you increase filtration fraction, what happens to the oncotic pressure within the efferent arteriole and then subsequently the peritubular capillary? So as more peritubular capillary oncotic pressure that raises, simultaneously more stuff is basically just getting dumped into the proximal tubule. Together, that results in increasing resorption rates within the proximal tubule. So glomerular tubular balance is the glomerulus talking to the proximal tubules, and what happens in one will be mirrored and paralleled in the other.